recording.
Okay.
Okay.
By the way, do you see the big slide and not the presenter thingy?
Yes, yes.
Oh, okay. It looks good. Okay.
Great, thank you. So thank you, Chen, for joining us and sharing your work with us. So I'm going to introduce you. Chen is an associate professor in the Integrated System Engineering Department at the Ohio State University and a core faculty member of the Sustainability Institute. His research involves computational optimization, especially MIP and MIP-inspired approaches. Applications include power systems, machine learning, logistics, and manufacturing. And today, again, we have a talk about disjunctive cuts. So thank you, and please begin.
Margarita, thank you so much. It's an honor to give a dot talk. It's so nice to see that, something created under unfortunate circumstances is still running and beneficial all these years later. So this talk is about, yes, disjunctions, but simple ones this time. And some let's see, can I get the slide to change? All right, a little bit of motivation. Why care? Well, at the least, I hope to make this talk entertaining. There's always this kind of trade-off between what's cool and what's useful, right? It's sometimes more severe, sometimes less. And in the cuts, I roughly say this. So there's a lot of cool cuts. Some fraction of them are practical, and some of the practical cuts aren't so interesting. And hopefully we can do this. I say hopefully this is a little undercooked. We have ongoing work, and I'm happy to just sort of share it now and take the risk, so to speak, because it's more fun that way. What's life without risk? From my perspective, the history is a long and winding road, and I think it ties into an explanation, at least how I see it, hopefully not too confusing. So I graduated from Berkeley in 2015, and at that time I started thinking about intersection cuts, and I brought my ideas over to Dan Beanstalk at Columbia, and we started working, and later on pulled in Gonzalo on the project, who's a student at the time. And so intersection cuts developed in 71 by Egon, and the idea is geometrically very elegant. So I'll use kind of a bit more of a modern presentation, which is that the goal here is that we're thinking about the non-negative orthant. As originally posed, you take any basis and the corresponding simplicial cone of a polyhedron, but you can kind of renormalize that cone to be the non-negative orthant. So we have a polyhedron that has one extreme point at the origin, and then its extreme rays are just the axes. Okay. So the intersection cut has the following setting. What if we punch out a convex region that contains the origin? In this case, we have an ellipse. So I subtract an ellipse, and I would like to know what remains and how to convexify that. So in this case, I take a bite out of this cheese, so to speak. I guess with the yellow color, it might be American cheese or something. So you get a non-convex region, right? You sort of can trace that curve of the red shape and how to convexify. Balas's intersection cut takes the intersection points, hence its name, of that what we consider now an S reset of that convex region. So here I mark that with blue stars. So it's the intersection of the red with the extreme rays or the axes of the yellow region, the non-negative orthant. So where does the S reset make contact or intersect with the axes? And here we have 2 points, right? And they're orthogonal axes, so we have linear independence in making the cut. And the calculation for this is over on the right. The lambdas are the step sizes. After some normalization, we can think of that as the distance from the origin up to that star with each respective axis I. And then you have B's and A's that come from the description of the basis. But here we have something a little bit simpler, right, with the non-negative orthant. So detail is not super critical. So that is the unique facet when you subtract a bounded set. there wasn't a formal proof of that in the paper, but we threw one in ours. And so if you subtract a bounded convex set from non-negative orthant that contains the origin, then you just need one cut to convexify. Okay, so that cut captures this information in some sense. Now I said bounded. Well, when we were looking at polynomial optimization, our S3 set of choice was unbounded sets. We were using cones. And so the mouse has a very big mouth, right? It takes an infinite bite of the cheese, of the infinite cheese. And so what happens to the formula in this case? Well, x2, the axis, is now entirely contained within the forbidden set. And so if we take that lambda parameter and move that to infinity, in this original paper, Egon tells us to set that coefficient to 0. And geometrically, one can think of fixing yourself at the finite intersection point, marked with the star here, and tilting the cut up along the x2 axis until you reach out to infinity, which will take you parallel. Right? So in other words, make it parallel with the x2 axis. That's what you get when you have a 0 coefficient for x2. So that was the cut we had been deploying in the context of polynomial optimization. We were applying these intersection cuts, and we're thinking, well, how do you make this better? Because if you look at this picture, well, there's a whole lot of red intersect with yellow region to the right of the cut. And it seems like we should be able to tilt this. So I ended up cooking a formula. That's my thumbs up for the formula up there, which is the simple idea that, well, whatever finite intersection points you have, anchor your cut there. And then that still gives you some degrees of freedom with the infinite intersection points. With those degrees of freedom, you take your cut and then you tilt it until you hit the lip of the recession cone, respectively on each dimension. So in this case, you have the blue cut, and then we can just kind of rotate it clockwise until we hit the lip of this convex set, this recession cone, right? So now we can cut out some more region. That is the gap between the blue and the green cut. It turns out that this idea had been explored a few times before in the literature, with the origin coming in the context of polyhedra and mixed integer linear programming from Fred Glover. He had named this the negative edge extension convexity cut. And the intuition for this is that, well, if we trace out that green cut and look at its intersection point with x2, the blue cut went out all the way to kind of an infinite intersection, or intersection at infinity with x2. And then you kind of loop back around and hit a negative point along x2, right? So the intersection point is at some negative value of x2 here, hence the term negative edge extension. And convexity, I think, referring to the S reset. So I had this procedure that kind of rediscovered this principle in the context of nonlinear S3 sets. And the other nice thing is that one can kind of rotate independently, sequence independent. So you recover a unique facet in this way, right? The unique has some nice properties I'll talk about later. So the natural question for me was, well, are there other tiltings? And so like, what do the other facets look like? And how many are there, right? In what cases do you only get one facet? Because here we had a very clean story. If you take out a bounded set, there's one facet, it's Egon's cut, right? But here, well, when is one enough? When do you get more? What does it all look like? So maybe around 2016, I started presenting our work and started asking this question, and got a response actually from Felipe Serrano, who is actually a former .talk speaker, right? And he pointed me to this work by Sen and Sherali, who again in that looked in this polyhedral setting with mixed integer linear programming and answered to a large degree these questions, and I'll go over this. And at the same time, Alex and Diego had been working on along lines of disjunctions, and they had heard my question, and we formed a super team with these 5 folks: Gonzalo, myself, Felipe, Alex, Diego. but we kind of had many abortive attempts over the years from maybe, I don't know, 2017 or 18, and then COVID hit, and then, abandonment. So the idea had been dropped for a while, and it was thanks to Alex reviving it, and also thanks to Air Force funding this, Alex's efforts. He brought on a student, very importantly, a student with the energy to actually get things done, Connor Johnston, and now I'm going to report on the results we got since then, with many thanks to initial efforts from Felipe and Gonzalo. So Connor has gone through a lot of the necessary torture to advance beyond these giants, and in the process has grown a nice beard. The beard is since even longer. We also have leaned heavily on another paper by Junhak, Mohit, and Jean-Philippe. And they developed this in the context of cardinality constrained linear programs. They actually ended up rediscovering some of the results of Sen and Sherali and adding an additional twist that we've discovered to be very useful. So some background. Let's start with the Sen and Sherali results and definition of title term, right? Simple disjunctions. Okay, so disjunctions, right? Ors, one constraint or satisfy another or another. Now, when each term, each constraint set is defined by a single linear inequality or half space, we'll call that simple. All right, so either satisfy one linear inequality or another or another. And our point of interest is non-negative orthant over these disjunctions. So one can write it as follows, and particularly the closed convex hull, so we can generate cuts. So what is the closed convex hull of non-negative orthant over these disjunctions, right? The union of each disjunctive set. In the geometric setting I gave, it actually has a very clean description, which is equivalently, we can define C as non-negative orthant minus the polyhedron where you just reverse all of the inequalities of the disjunction. So the polyhedron is essentially arbitrary, right? So what happens if let's say it takes out the origin as well. What happens if I have a polyhedron that takes out the origin and I try to convexify what's left of the non-negative orthant? Okay, so that's the setting, and it applies to generating cuts in a very general manner in integer programming, for example. So this was answered in large part, a very large step taken by Sen and Sherali here. Some notation. So first, J plus. These will be the variables where all the disjunctive coefficients are non-negative. It actually has a super nice geometric definition, which is those axes that have finite intersection points. Okay. So that is positive finite intersection points. And then the J minuses will be the disjunctions with strictly negative coefficients throughout all the disjunctions. Those are the ones with intersections at infinity. So geometrically, we just split up in terms of finite intersection points at infinity. There's a little bit of algebraic sorting out. It turns out you can essentially ignore all the other variables where you have mixed signs. We have a little lemma for that. So in our kind of slightly slicker treatment, we describe the reverse polyhedron as follows. So you have basically two sets of inequalities. One of them tells us about the finite intersection points. So these are for the J plus variables, and you have a simple lower bound, the pi j greater or equal to gjj. As the coefficient goes up, it's reciprocal to the distance, so you get closer and closer to the origin. So as you get further from this lower bound constraint, you are moving towards the origin and away from the finite intersection point, weakening the cut along that axis. So when it's equal, that cut is strongest. You're anchored at the finite intersection point. And then for those intersections at infinity, you have these pairwise constraints from each intersection at infinity. You can think of a vector going to each finite intersection point. So in this example, for example, you have this green star. You can draw a vector from the green star up to the blue star, right? That will be one direction. But there are potential other notches along the negative side of x2 in higher dimensions where you can kind of pick among these and you'll get this interesting sort of combinatorics that I'll talk about. So this is the reverse polar. It's a polyhedron that tells us the shape of the valid coefficients for cuts of our object of interest. And it has this nice structure. Another very interesting result provided by Sen and Sherali is that the knee cut is in fact the best facet of C according to essentially arbitrary metric norm, so like 2 norm or something. So the Glover result is very strong as a starting point. But my thumbs up question kind of still remains. So there's still a little more to do here and why I'm giving talk. So what do the other facets look like, right? So the reverse polyhedron does tell you that implicitly, but how do we explore it? This is partially answered in this AD's paper, which is that if you give them a rank ordering preference of your variables, so I like x3 the best, and then x5, and then x2 and x1, then one can find the corresponding facet for that rank order. And this procedure is faster than ordinary simplex pivoting. But it's not enough as a roadmap across all of the possible facets. I mean, the naive approach would give you factorial exploration. And likewise, on this question of, well, how many of these things are there, it's unknown, right? It remains unanswered. So that gave us, and particularly Connor, something to do. And okay, first point, there really are a lot of facets. I didn't lie to you. I wouldn't do that to you in the title, right? There really are a lot of facets. Okay, here's an example. I cooked it up and I found it very funny when Connor said it was terrifying in its implications, because it's rather simple and it shows some things that were pretty neat. So we construct as follows. It's a 2-block matrix describing the disjunctions. The left block is identity. Here I give you 3 disjunctions, but it applies to n disjunctions, right? So left block is an n-sized identity matrix. Right block is negative identity, and all the zeros we fill in with -2s. So that's it. That's our disjunctive set. Now it turns out that for all the plus variables, that is the left block, we assign a coefficient of either 1 or 2. And on the right block, we assign coefficients of either -1 or -2. Doing so, we can show that all such choices, except for the all 2 -2 solution, is a facet. In fact, there's a little bit of cool geometry here where if you set it to 1, you actually take the finite intersection point. That is the left block. And if you set it to 2, you take a step halfway to the origin. So as long as you don't step back from all of the finite intersection points, as long as at least one point is anchored, then you have a facet. The -1 and -2 correspond to tiltings. So anyway, even in this setting, which is, you take an LP solution, right, from your relaxation, and you only consider a simplicial corner, and we take out some simple disjunctions. Even here, you have exponentially many facets. So we can't just add all the cuts corresponding to this, not in general, right? We need some sort of judicious selection. So some natural questions. Can we, for maybe fixed Q, you tell me you want 10 cuts or something, can we generate the 10 best cuts in some sense in polynomial time? So here's where I have to be a little bit risky. And I will say, I think our answer is yes, but we'll have to prove it, right? We have the pieces. Some things I can say definitively, special cases. So with 2-term disjunctions, we establish a linear number of facets that is just 2 constraints, either constraint 1 or constraint 2. This condition generalizes splits. In the particular case of splits, then you just have 1 facet, right? So in general, you'll have a linear number of facets in the special setting. Also, if you fix the number of anchor points or finite intersections to 2, then there's a quadratic bound on the number of facets. So what makes this complicated is potentially the combinatorics of having to explore a whole bunch of on-offs on the finite intersection points, it seems. So there's additional bad news, because even in these cases, okay, cool, there's a linear number of facets, run simplex. I mean, who cares about multi-term disjunctions? Well, apparently we should care, given the last talk, right? But even there's a lot of bases. So more depression. Here is a similarly terrifying example. So here's just 2 disjunctions, and we would normalize right-hand side to 1. The first disjunction is composed of 1s, 0s, and -1s, kind of just alternating. The second disjunction is composed of 0s, 1s, and a number that increases linearly. In this case, we can demonstrate that there are a linear number of facets and an exponential number of bases. So naive primal simplex on the reverse polar is at risk here. We may have to be more clever to explore this, even in simple cases. Okay. So we're exploring the many facets. We really don't want to explore the many bases. That's not going to get us anywhere computationally, or probably not much. Right? All right, so some negative news, but do not despair. We have the power friendship. And we have these 3 different components that we put together. Actually, I've realized that I run a little bit longer than I intended, so I apologize, but let me go very quickly. One of the ideas is you can do a nonlinear transform and take your finite intersection points and infinite intersection points, construct a bipartite graph, and start pointing arrows to represent binding constraints between these. There's some technical matters that I'm skipping over, but we've solved one of the issues with this very clever construction from the trio. And our idea is attempting to construct an algorithm to pivot between adjacent spanning trees and thereby hop over degeneracy. And I believe we have achieved that. What's interesting is that the unique cut is the unique facet where everything is kind of anchored where it can be. That is, all the left side inequalities are equals. And you kind of play around with this graph. I'm gonna have to skip the third component entirely, but we have this idea of simple disjunctive cuts here, which came from Balas's 1970s work. And there's an observation that if you scale your disjunctions, you can keep the set, just multiply each of the inequalities by some positive numbers, the same thing geometrically. But you can actually manipulate these cuts, and essentially the scalings will act as Farkash multipliers. So it gives us an additional perspective in the cone of multipliers on playing around with these cuts. So the dual transport, the scaled idea, and all of this, they all come together to allow us to work on an algorithm of exploring through these graphs. I apologize for the mistiming of this. That was my first time doing this particular one.
You
And
have a
here
little bit more time. I don't know how much your time. You have about at least 5 more minutes.
Oh, really? And the timer on this thing said 30, so I got scared. Oh, okay, we're good. Yeah, PowerPoint misleading me. Okay, let me go back a little bit then. Here's the formula, which is that you can take your disjunctive coefficients, and we take the maximums on the left side and the minimums on the right, and this is a valid inequality. What's cool is that you get something called the standard intersection cut. It dominates the restricted intersection cut. It is weaker than the unique cut. Okay, but it's a very simple formula. You just need essentially like a sort function or something a little bit simpler than that. And so we can play around with this by playing around with the thetas. This is done in CGLP, but here, if you play around with thetas, you get a nice closed form expression, computationally nice, right? Analytically nice as well. So we have the following result, and it's best explained with this example. Here's a bunch of disjunctions, and we put it in this sort of normalized form. So left side is identity, and right side is whatever. Something that I've termed diagonalization in honor of its inventor. Right? It turns out every simple disjunctive system we can always renormalize in this way. So using this max-min formula, the coefficients, we want the maximum, and the maximums are attained. So for x1, it's just x1, the first disjunction. For x2 is the second, right? The rest are zeros. Now for the minuses, I've sorted these. It's a nice example. So that x5 is the maximum, it's the least negative term. Okay, so we get the following cut, which is that let's say if we set all our thetas to 1, then we will get just a bunch of 1s for x1, 2, 3, 4, and then a bunch of -1s for x5, 6, 7, 8. Now, we can scale these disjunctions, and it preserves the system. It's the same C set that we care about. But the scaling will result in a different cut. We define a simple scaling operation, which is the minimum scaling corresponding to targeting a single entry. So currently our cut is just a bunch of 1s and -1s. Now, what if we wanted to make the x6 coefficient a -6? As you see from the top left in the formula, is a maximum function. So we'd have to get this -1, and if we can scale these disjunctions, we can push that coefficient and tilt more in that direction to -6, strengthen the cut. So the minimum theta necessary to do that is to go 6, 6, 1, 1. It turns out that geometrically what we've done is through theta space, move from the original unique cut onto another facet. We can show that every simple scaling is a facet, though not every facet is a simple scaling. But this gives us a starting point and sort of branching from the unique cut and exploring other facets. There are additional complications in this procedure because simple scaling is not sufficient. And if you sort of pursue this path, you may end up with the equivalent of degeneracy in the theta space. So for that, we tortured Connor to go through a very deep and difficult set of papers from Provan on exploring polyhedra of networks. The insight of the trio was to convert the reverse polyhedron to an equivalent dual transportation polyhedron. That is a bijection of their extreme points. And so with this graph structure, I believe that we should be able to, or we have constructed or jury-rigged our own version of Provan. That's an efficient way to skip through some of these degeneracy issues, both in the primal and the theta space. So yeah, I'm done. Thank you.
Thank you so much, Chen. So